Watkins up to the podium here so that we can give up the Bullitt Scholarship and Bullitt Prize for Best Paper, Best for Undergrad Paper. So I would also like to invite Bryn and Lydia up to the podium.
Scholarship.
So, everything here. This is scholarship. And this is for best paper is for Lydia, which is currently in revision, but given her very first paper. Active collected nuclei on the cosmic web. So that's what the paper is on, and so we're very happy that's got the prize. And Bryn is working very hard on her Fulbright application, which is due in TikTok later, but not today. So yeah, very glad for these two to get these. So thank you so much, Lowry.
A few words about my maternal grandfather. He was 4 years at Princeton, University of Louisville Law School. He's the most famous student to ever come out of the law school. His portraits there. He became Solicitor General of the United States under President Taft. At the time, he was the youngest Solicitor General in U.S. history at 1912, 39 years old, and he had the most cases in front of the U.S. Supreme Court, 53 at the time. His hobbies were mathematics and astronomy, and he hired a book dealer in New York and in Berlin, Germany, to find first edition astronomy and math books. For 50 years, he collected them. After he died, his widow gave them to the University of Louisville in the rare book department. The most famous book is Principia by Newton, with Newton's handwriting on the margin. I've seen the book. They brought it out to me. He was a pen pal with Einstein. As far as I know, he's the only person to show Einstein how you could skip one step in the energy equation. And he was an amateur mathematician. Nobody else showed Einstein that. They never met, but they were pen pals. So I endowed things here at the University of Louisville in memory of my grandfather at the law school. Food court team, lecture, award for the best paper, a scholar, book fund, and he ran the biggest bank in Kentucky and the biggest law firm in Kentucky, which probably made him more powerful than the governor of Kentucky. He died in tomorrow, 58 years ago tomorrow, October 3rd, 1957. The very next day was Sputnik. He missed Sputnik by 1 year, and he would have loved being alive when that happened, but unfortunately missed it by 1 day. So thank you all for coming, and appreciate it, and enjoy the lecture.
I am absolutely delighted to introduce Dr. Saavik Ford, Saavik Ford, from City College of New York.
University.
University of New York. I always get the, sorry.
Sorry.
graduated in 2003. I was at her graduation. We're grad school buddies from back in the day. And then you went to CUNY, the electromagnetic place. What is it?
Department of Terrestrial Magnetism.
Department of Terrestrial Magnetism. I just always like both the magnetism place. And then you went to South Carolina for a year,
Yep.
and then got appointed as professor at CUNY. So I've been learning about black holes from her, and now we all can. So I'm absolutely delighted. Give her a big hand.
Let me steal that. Just in case. All right, so hopefully everybody can hear me okay. I am actually equally delighted to be here and for Ben's students. No, I don't know any stories about him from when we were in grad school together. So I'm very pleased today to be talking to you about wiggles from the universe and how we are starting to feel our way around using gravitational waves, in addition to seeing our way around using light. And so this is a pretty long title. The short version is, how do we know? How do we know anything at all about our universe? Because as was alluded to by our benefactor here, humans have never gone farther from the Earth than the moon. And that's really not very far in the grand scheme of things. If you go over to the planetarium, you can see the size scales of the various bodies in our solar system. And if you think of the Earth as something that's about the size of a basketball, then the moon is about the size of a tennis ball. And it's sort of halfway back in the room. And other than that, we've never sent people to go explore. And the way that we have obtained almost all of our information about the universe is because the universe sends signals to us. And it sends it in a number of different important ways, but they're all very limited. And we've known about some of them for longer than others, and I'm going to tell you a little bit about them. So the first way that we have gotten information about our universe is through light. And this is a mechanism or a messenger that's brought us information about the universe since the first time we were human, and even arguably before, right? You go out and you look up into the night sky, or you go out and you look at the moon during the day, or at night, or the sun. And basically, as we look around the world, we see evidence of humans everywhere inquiring into the nature of where this light is coming from and what it is doing and what it can tell us about distant places that we may never be able to reach. We also do sometimes get meteorites, and these are rocks that fall to the Earth. They only come, as far as we can tell, from within our solar system. So they have a pretty small reach for where we can get that information from, but they are nice when they arrive because we can do things like actually take them apart in a lab and learn things about them. And that's the only stuff that we have been able to do that with, except for, again, the handful of samples that we have gone and gotten and returned. There's also these things that are a little bit less well known, cosmic rays. These are charged particles, and they actually come to us from distant galaxies or other parts of our galaxy. And they were first detected in 1912 through balloon flights. People thought that if you went farther up in the atmosphere, you would get farther away from radioactive sources on the Earth, and so you would see less and less radioactivity as you went up. And the first balloonists went up, and they found out that you got more. And they went, well, those must be cosmic rays. And so today we see them, and you see them as charged particles swirling around magnetic field lines. And this is going to come up again, but so you may have seen images like this. And so these are actually particles, very small, that have come to us in many cases from outside of our galaxy. But they're very difficult to capture and study. We also have a messenger called neutrinos. And you might have heard of these, but you may not. They're pretty rare, or rather, they're not very rare, but they're very rare to detect. You have many, many, many orders of magnitude of them running through your body right now, but the odds that they're going to interact are about 1 in 10 to the 38 against. If that number means something to you, congrats. Even I have to figure that out. And so in order to detect them, this is a neutrino detector under construction, Super Kamiokande in Japan. And if you can see, that's a little rowboat with 2 people in it. And this entire tank is going to be filled with water. And they can expect to get a few neutrinos a day. They're very, very difficult to detect. And they mostly come from nuclear reactions in the cores of stars or from other very, very high energy processes. And so they do come from far away, but you'll notice that meteorites, cosmic rays, and neutrinos are actually all delivering some kind of particle to us, somehow. We also have these things now, gravitational waves, and these were actually first directly detected just 10 years ago. As of September 14th this year. And so I'm not going to share an image with you right now, but I want to focus on light and gravitational waves because they're the ones that arrive to us and they bring us information and energy, but they're not actually transmitting anything physical to us. So light is the one that you're all at some level familiar with. And we've seen it, we've played with it. You have probably looked at your reflection in the mirror or interesting reflections through a glass lens or a glass of water. But what light really is an electromagnetic wave. And all that really is something that is wiggling, right? So something is wiggling. It is an electric field and a magnetic field, and that is what is producing light. But we know that there are different colors of light, and indeed, we've known since Isaac Newton that some of which are more refrangible, more bendable than others in things like glass and water. And the light rays, how bendable they are, depend on their color. And it turns out that that's because they are different wavelengths. So if you look at this wave, how far apart the peaks are is the wavelength, and you can shrink that or expand that. It's just arbitrary. But it turns out that our eyes can only see light in a very, very narrow range of wavelengths. And so up here is a much fuller range of wavelengths. And you can see that there are waves that might be a whole meter or a yard across from peak to peak. And they get smaller and smaller down to the width of a hair, down to less than the width of a hair if you're looking at visible light. And visible light comes in, of course, many colors. And then they get smaller and smaller from there in down to smaller than the width of an atom. So it turns out that although these things are all the same wiggles, but with different wavelengths, because they have different wavelengths, they interact with matter differently, which is why our eyes can only see visible light. But if we go and we look out into the universe, you may recognize the Hubble Space Telescope. It operates mainly in the same wavelengths that our eyes see, a little bit longer wavelength into the infrared and a little bit shorter wavelength into what's called the ultraviolet. And so you've probably seen pictures from the Hubble Space Telescope of the Hubble Space Telescope, and it looks kind of like a telescope that you expect to see, and the pictures look kind of like normal things. So, for example, you've all probably seen this beautiful image from the Hubble Space Telescope of the pillars of creation in the Eagle Nebula. And this is what we know now as a star-forming region. So the gas clouds, we mostly don't see the hydrogen there, but we do see the dust, and that's why they look dark. And if you try to look through them, you can see that there's fewer stars behind them, not because there's really fewer stars, but because the light from them is being absorbed. And they're quite beautiful, but it's a little bit hard to see what's going on inside of them. It turns out that if you look at slightly longer wavelengths into the infrared, as we can with the James Webb Space Telescope, JWST, you can see through clouds of dust. And so JWST has also looked at the Eagle Nebula, and you get a different viewpoint. All of a sudden, the dust is much more transparent, and you can see how many stars are actually behind there. And so by looking at different kinds of light, astronomers are able to wring more and more information out of this messenger that brings us what we know about the universe without ever having to leave home. But you might have noticed there are some other wavelengths on here. We can also use X-ray telescopes. And so this is a picture of the Chandra X-ray telescope, which is nearly as old as the Hubble. And this is an image of the pillars of creation with the infrared from JWST, and then overlaid in the multiple colors are the Chandra X-ray images. And so you can see that there are lots and lots of multicolored dots in this image. There are some that look like they might be inside of those pillars, and they probably are. There are some X-ray sources that are forming stars, that are producing jets, that do give off some X-ray emission, but many of them are actually, and this is another thing that we learn when we start to look out into space, they are actually distant galaxies that are X-ray bright, that are past our own galaxy. And we don't actually have much in the way of depth perception automatically. We have to figure that out as astronomers, what's in front and what's behind, what's nearby and what's far away. And we don't always have clues that we have locally. I kind of know how big a car is, so I can judge based on how big it looks, how far away it must be. But we don't always know what the object is and how big it ought to be. And so we have to find other clever ways to do things like measure distances. You might also notice that there's a bit of a glow off to the, from your perspective, left-hand side of the image in orange. And that is towards a part of our galaxy that we're going to come back to. There's another part of the spectrum, the electromagnetic wiggles, that are very, very long wavelength, that are radio waves. And we have radio telescopes at many different wavelengths of radio waves that also tell us information about our universe. And this is an example of information that you can get from radio waves. You can tell which way the magnetic field is pointed and how strong it is, because if you try to run a radio wave through a magnetic field, it will, being an electromagnetic wave, respond to that field. And so all of those gray lines that you see are a map of the magnetic fields that exist inside of these pillars of creation, which were obtained from radio wave observations. But all of this we understand based on light. So I want to give you a sense of where these electromagnetic waves come from. And to do this, I've taken a few stills from PhET simulations. So if you are an educator and you haven't heard of these before, I encourage you to go check out their website. And this is a simulation that you could play with. And we have a radio station with an electron sitting in an antenna, and it is going to be transmitting, and that is over here on your left. On the right is a receiving antenna, which also has an electron in it. And if I wiggle the electron, I get an electromagnetic wave. And that transmits information, and if I have another electron, it can be wiggled by the wave and pick up that information. And so this is actually how radio transmissions work, but this is also how all kinds of electromagnetic waves are detected here on the Earth. If they're in the radio, this is basically how we do it. For visible light, there are electron reactions that are happening inside of your eyes, or if you have one of these, right, there's an electronic camera in here. By the way, you can thank astronomers for that. CCD technology is what's in your camera. It was cutting edge when I was younger. So all you need to do to make any kind of electromagnetic wave is wiggle an electron. And depending on how fast you wiggle it, that's what your wavelength is going to be. So anytime you want one, you just do that. Seems pretty easy, right? So gravitational waves seem like this very strange, esoteric kind of wave, right? People talk about them as a consequence of Einstein's relativity, and they're some kind of crazy outgrowth of gravitational something. But actually, all gravitational waves are the waves that you get not when you wiggle an electron, but when you wiggle a mass. Here, I'm making a gravitational wave. No one will ever detect it, because it turns out that the reason why gravitational waves were the last messenger that we were able to directly detect is that gravitational waves have been detected from, first, binary black holes. So two black holes orbiting each other. And gravitational waves come in and they look kind of like, in some sense, light waves or any other kind of water waves, right? Things go up, things go down. Gravitational waves are actually a little bit two-dimensional. So you can see that they will stretch things in one direction and compress them in another, and then do this, right? This is my gravitational wave impression, all right? And this is part of how we actually detect them, because what they're actually stretching is distance. So if I have two rulers and a gravitational wave comes along, it will stretch this ruler and shrink this one, and then it will shrink this one and stretch this one, and back and forth and back and forth. And so all I need is two rulers, and then I can get a Nobel Prize. So the problem comes when we realize that gravity is extremely weak. And you may not realize this because you're all sitting here and not flying off into space because, hey, gravity. But when you compare it, right, the gravity that's holding us here is the gravitational pull of the entire planet Earth. But I can defeat the gravitational pull of the entire planet Earth with a magnet that's like this big. Watch. It doesn't fall. I have taken away all the power of gravity with just a teeny tiny magnet, the gravitational pull of the entire planet Earth. And so gravity is actually a very weak force, and that's what we mean when we say gravity is weak. We think of gravity as strong only because the Earth is very large. But you might notice, especially the astronomy students among you, that gravity turns out to be really important. And how could it be so important if it's so weak? And the answer is, if you've ever played with magnets, you know that they can both pull, but also push. Gravity doesn't know how to push. It only knows how to pull. And so if you have things that can push and pull, if you toss a bunch of magnets together, they'll naturally sort of find a way to cancel each other out. And the same thing with electric fields. If you have positive and negative charges, they'll find a way to cancel each other out because they can do this push and pull. So even though they're much stronger, because they can do both things, they add up to nothing. Gravity, although it is extremely weak, always pulls in the same direction, and it never gives up. And that is why gravity seems very strong and ends up being very important to shaping the universe around us. But if you're trying to directly detect gravitational waves, it's a little bit of a problem. So I'm going to talk to you about how you beat gravity, even though it does continue to pull at all times. And we're going to have to think for a moment here about the idea of escape velocity. And this is just the idea that you can get off the Earth. We've done it, right? Sputnik, Apollo, we did send some guys to the moon, right? And we've sent probes to Mars and beyond. But the way that you do that is you move really fast. And so there is some speed. And again, I don't play for the Cardinals or the Yankees, so I can throw this as hard as I can, and I'm still not going to beat the gravitational pull of the Earth. But, you know, if I stick a rocket behind it, I could. And I could make this thing go at the escape velocity of the Earth and get away. And that's because the Earth has some gravitational pull, and it's strong, but it could be stronger if I was a supervillain and I decided to take the Earth and crush it and made it smaller. Then where we are standing here on the surface of the Earth, if we could somehow be supported at the same distance above the surface of the Earth, we would actually feel the same gravitational pull, because I haven't changed how much mass is in the Earth, and I haven't changed how far away we are from the center of the Earth. But if I've crushed the Earth, then the surface is closer to the center. So if I were allowed to fall to the surface, I would experience a stronger gravitational pull, and to escape that new surface, I would need a larger escape velocity. If I kept going, I could keep pushing the escape velocity up. And so if I were to take the Earth and crush it down very, 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 very small, I could, in principle, make the escape velocity the speed of light. And that would be tough because, like, we live here and it would be sad if we couldn't go anywhere anymore. But also, right, light is this messenger that gives us everything that we know about our universe. And so if you have a black hole, it doesn't give off any light. And so how can you learn anything about it? And the answer is, it is a mass, and if you accelerate it, it will give off a gravitational wave. And that we can hope to detect. But because gravity is so weak, we are going to have to work really, 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 really hard to make that detection. And so that is what these good people did. So these are photographs of LIGO, the Laser Interferometer Gravitational Wave Observatory. And there are two of them, and you will notice that they are basically two things in straight lines at right angles, because all they are really, 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 really precise rulers. The two arms on each of these detectors is 4 kilometers long. So they are constantly measuring the distance down the arms. At the end of each arm is a mass that is experiencing gravity. And what they're actually doing is inside of those two arms is a vacuum tube, and it is evacuated. It's one of the best vacuums that we've ever created. It's better than the vacuum of near-Earth space. And they're shooting lasers down the arms. And so if you want to work at LIGO Labs, yeah, it's really cool. And so they use the length of the arms, and they can constantly compare the length of the two arms to each other. Because you might wonder, well, if you're stretching or shrinking your ruler, how do you even know that your ruler is changing length? And the answer is that you don't. So what you have to do is compare the lengths of the two arms at all times and watch for them to not be the same. And so that is what these two gravitational wave detectors have done. And these are two detectors that people have been working on for literally decades. So they were working on them for something like 40 years. before they made their first detection. And now there are also detectors in Italy called Virgo and in Japan called Kagra, but they are still not as precise or sensitive as these LIGO detectors. And in order to understand where things are coming from in gravitational waves, you actually need both detectors because they're in two different places on the Earth. And so as gravitational waves come, they're going to hit one detector first and then the other one, however long light takes to travel from one detector to the other, or something like that. And by knowing what time the waves arrived at the different places, you can triangulate where in the sky it might have come from. And so if we don't have both detectors, we actually can't tell even where we're looking. It's just sort of like sitting there with our eyes closed and your ears open and hoping for the best. So about 10 years ago, LIGO detected GW 150914. So that's the event that happened in 2015 on the 9th month, September, on the 14th day. And this is actually a diagram of what happened. So the gravitational wave is that blue and orange waveform that you see, and we interpret that as being caused by these two very dense black holes spiraling around each other in a binary, getting closer and closer and closer together. And as they get closer and closer together, they are giving off energy. For the physics students among you, right, you have an orbit, the orbit is shrinking, it's losing energy. Where is the energy going? It's going out in the gravitational wave. And then when they get close enough, they're actually touching and they merge. And then you have this like very angry, upset, excited black hole, and so it has to sort of shake itself loose, kind of like a bell that got hit with a hammer. And so then we call that last phase ring down. And at the end, you have a very large black hole by black hole standards. This is actually the sound of these black holes merging, these first two. Oh, or not. Hang on. All right. I don't think we're going to get that. Okay, so what you would have heard is something that sounds a little bit like a... The frequency for the musicians in the audience, right, is also inversely related to the wavelength. As the frequency goes up, the wavelength goes down, and you can see that wavelength shrinking. Those peaks are getting closer together because the black holes are getting closer together in their orbit. And so the frequency is going up or the pitch is going up. And so this process is actually called a chirp because it sounds like one. And this is actually basically in the range of human hearing. If you translate this directly into sound at the same frequency that it was observed at, you actually get an audible wave. And so these black holes that LIGO detected were 29 and 36 times the mass of the sun. So that's kind of big, right? The sun is like 1 million times the mass of the Earth. And then we're talking 29 and 36 times the mass of the sun. These are pretty sizable masses, but they're extremely compact and small, and so they're just over 100 miles across a piece. At this point, actually, as of just a few weeks ago, LIGO, Virgo, Kagra have formed a consortium, and they've agreed to cooperate. And these are all of the black holes that have been detected by that collaboration here in blue. And you'll notice they always come in pairs. So there's two black holes, and they merge, and they form a third black hole. And so basically, you always see two blue dots and a gray arrow that goes up to another blue dot. And we're up around 200 total binary black hole mergers that have been detected. You can also use gravitational waves to see somewhat smaller mass, somewhat less compact, but still absurdly strange objects that we think are the remnants of stars after they die, called neutron stars. And those are down in orange. And you can see that it looks like maybe there's more black holes than there are neutron stars, but that's not really true. Mostly, the more massive something is, the bigger a bang it makes. And so the farther away we can see it. Neutron stars are actually far more numerous than black holes, but because they are a weaker signal, we can't see them unless they're pretty close. And so this is not a true census of what is existing in the universe, and this is the kind of thing that scientists always have to think about. When we look at the universe around us, the messengers are bringing us information, but they have their own agendas, right? They bring us biased information, and so one of the things that we always have to do is think about, why is this information coming to me? How am I getting it? And what are the biases that it arrives with? And so for gravitational waves, the thing that they are biased to tell us about are the most massive things. And I do want to highlight, up at the top, there are some that are up to 200 solar masses, so 200 times the mass of our sun, which is pretty big. There are stars that reach up to about that mass, and when the most massive stars die, they leave behind black holes, but we don't think that they leave behind black holes that have masses much over 50 times the mass of the sun. So actually, there's quite a lot of black holes on here that are more massive than that. And those require explanation for where they come from. And so, where are all of these things coming from? So one possibility, and the one that people have thought about for the longest, is a pretty logical one. Those of you, I know that there's a fair contingent of amateur astronomers in the room. You know that there are binary stars. They orbit around each other. They are beautiful and enjoyable to observe. And if they are massive enough, when they die, they might leave behind a pair of black holes, and then those pair of black holes will become binary black holes. And right now, the light that they're giving off is giving us information and bringing us a message about what they are. But when they turn into a pair of black holes, there won't be any messenger of light, but there may be a messenger of gravitational waves to inform us about that. But that's the only way we're going to find out about them. So binary black holes from binary stars seems pretty logical. It's also logical because the most massive stars are very, very likely to live in binary systems. So cool. We could just do it all. The problem is what I said before. You really can't get past about 50 times the mass of the sun, which is a couple of lines down from the top on this one. There's a fair number of black holes on here that are more massive than that. And although I've made it sound like it's pretty easy for two black holes to spiral into each other and give off gravitational waves, that's not really so easy. If you take a black hole that is 10 times the mass of our sun and another one that is 15 times the mass of our sun, and you put them, one of them where our sun is and the other one where the Earth is, and you let them spiral into each other, it will take them 100,000 times the current age of our universe to spiral into each other. So that's bad. It's really hard to put stars really close together. It's hard to put them a lot closer together than about the Earth-Sun distance very often. And we do see quite a lot of binary black holes merging. And so even if you can put two stars close together, then how do you get over that 50 line, right? you could say, well, maybe there's a third one, but that's going to be even farther away. And so you start to run into problems very quickly if you just say, I'm just going to worry about pairs of stars. So another alternative is to look where there's just lots of stars and lots of dead stars. And so this is an image of a globular cluster, which is a very, very dense collection of stars that orbits our galaxy, and we have lots of these globular clusters. And these can have literally 1 million stars inside of the distance between the sun and the next nearest star to us. So very, very, very compact, right? 1 million times denser than what we have, than the area of our galaxy that we live in. And as stars live and die, they tend to sink to the center of the cluster because the most massive things like to sink to the center. And so black holes, being fairly massive, will end up in the center and they'll end up pretty near each other, and you might manage to pair up a couple of them that weren't originally having anything to do with each other. And so you could imagine doing that once and then maybe doing that again. And so you can start to build up bigger and bigger black holes this way. But there's a problem. When black holes merge, these gravitational waves that they are giving off carry away energy, but they also carry away momentum. And for any of you who have ever experienced a recoil kick or just any kind of equal and opposite force, if you have a martial art and you take a whack at a stack of bricks or boards or anything like that, right, you know that there's going to be a back reaction. And so when these waves carry away the momentum, they tend to give that final remnant a kick. And the kick can be substantial. And the kick can actually be so substantial that it is larger than the escape velocity of this cluster. So again, we come back to what is the escape velocity. So if you make a binary black hole merge in the center here, but the kick is bigger than the escape velocity of the cluster, it'll rocket out and it won't be able to find another partner, and you won't be able to make these ever more massive black holes. So maybe we need some way to keep them at home. And something that is 4 million times the mass of our sun is maybe massive enough to hang on to a lot of stuff. So this is a video of the center of our galaxy, and it's called Sagittarius A star, and it is the bright X-ray source that you saw off to the side of the pillars of creation. But this is a different way of looking at it, and all of this is, of course, using light. These are stars, and we're going to watch them in sped up motion. So you'll see the years change from here, and we'll watch them, and then we'll zoom in. So did everybody see that? So there was a star, and it was orbiting around a giant yellow cross in the sky. Oh no, wait, that's not really there. We drew that on afterwards. It's orbiting around nothing. There's nothing there, or at least there's nothing that delivers us any information through the messenger of light. But we can use the messenger of light, which is coming from this star, to observe that that looks an awful lot like one of Kepler's elliptical orbits, and that's exactly what it is. But the thing that is orbiting here is not a planet, but a star that is 10 times the mass of the sun. And it is getting tossed around as easily as a planet in our solar system. And so what you need to do that is something that is 4 million times the mass of our sun sitting at the location of that cross and giving off no light. So that basically has to be a black hole, and it has to be a supermassive black hole. But you'll notice that around that black hole, there are an awful lot of stars. And if there are stars, then there are probably also dead stars. And so we know that there must be stellar mass black holes also densely collected in the center of our galaxy near this supermassive black hole, even though we can't observe them with light. This is an artist's impression of a different galactic nucleus. So this is the center of a galaxy which also has a supermassive black hole that you see in the background. But this supermassive black hole is visible, not through its own existence, but through the shadow that it's casting on the gas that is accreting onto the supermassive black hole. This is what's known as an active galactic nucleus, or AGN, active galaxy. And that's active because we think every galaxy has a supermassive black hole at its center. It's just that most of them aren't busy eating. Some of them are. And when they are eating, you have gas that is trying to cram into a very small space because it is falling in, being drawn in by the gravity of that supermassive black hole. And so as the gas is falling in, it's heating up. You're taking gas, and it used to take up more space, and now it takes up less. If you compress a gas, the temperature goes up. And when things get hot, they emit light. And so this is why we see these active galaxies. But if you drop some gas into the center of the galaxy, there were already stars there, and there were already black holes. So you might wonder, right? I said that the reason that you can't take two stellar mass black holes and merge them and then make them find a partner and merge them again in a globular cluster is that the first time you make a merger, it's going to get a recoil kick and leave the cluster. In our own galactic nucleus, you could try to make a binary black hole, but watch how the orbits of the stars are behaving. Watch what directions they're going. Are they coordinated? Or are they random? They're going in every direction. They're like a swarm of angry bees. Getting two of them to pair up and make nice is really hard. So you could maybe get two of them to merge, but the odds are not great. So if you got them to merge, they wouldn't go anywhere, and you could then maybe find another partner. But again, the odds of them finding each other to make a binary that's going to actually get all the way to merger are just not great. But if you drop this giant gas disk onto that environment, then everything is trying to pass through this disk, it will end up being swept up by that flow of gas. And so now, instead of having a swarm of angry bees, you have an organized set of runners on a track. And it is much easier to grab your fellow runner or pass off a relay stick in that kind of environment. And so in this environment, you can make black hole binaries, you can merge them, and then they will stay there. And then they can find another buddy, and they can keep going. And so you can potentially break this 50 solar mass limit. And that's actually pretty exciting. The most massive black hole binary that has been detected so far is, oh, I see my mouse doesn't actually show. So all the way at the top in the center, you can see that there's one that's about 225 times the mass of our sun. And so even if you started with 50 solar mass building blocks, that is quite a few mergers that had to go into that thing. And actually it turns out that the most common size of black hole merging is 10 times the mass of our sun. So that's actually a lot of mergers. Or there's also an excess around 35. And the black holes that went into that most massive merger are about 105 and 140, which for those of you who are quick with the math is about 3 and 4 times 35. So if those were formed from these successive, what are called hierarchical mergers, it's very probable that they happened in an active galactic nucleus. And that is actually really exciting because that tells us a lot about the environment in order to make so many mergers in such a short period of time as the length of an active galactic nucleus being on and having gas falling into that supermassive black hole tells you a lot about those active galaxies themselves. So this is an artist's impression. The other thing that you might notice is that in this environment, these two black holes are surrounded by gas. And while black holes don't give off light, gas does. And so there's a hope in this environment that we could get both messengers from one of these events, where you see two black holes in gravitational waves, and then because of that violent merger, it impacts the disk, and the disk can then give off light signals that can bring us that message as well. And so the idea behind all of this is that we can observe many things from many different angles and learn things about them. You might have noticed, though, that I've been talking a lot about stellar mass black holes, things that are 10 or 50 or even 200 times the mass of our sun, but that's not 4 million times the mass of our sun, like the supermassive black hole at the center of our galaxy. We think that those black holes sometimes also merge and find each other, and they will also give off gravitational waves. But because they are so massive and so large, they move much slower, and so their frequencies are much lower. And so we detect gravitational waves here on the Earth only up to about 200 to 300 times the mass of the sun. Basically, those black holes can be detected from the ground. After that, it turns out that the Earth shakes so much from earthquakes and just little tiny seismic noise that we never notice as humans, but when you're trying to measure distances that are smaller than the width of a proton, you notice. And so basically there's a limit to how big black holes we can see from the ground. But if we go to space, we can make our arms as long as we like. And indeed, there is a plan to launch the Laser Interferometer Space Array, or LISA, which will have arms that are millions of kilometers long and will be able to detect binary supermassive black holes. And so that is at a much lower frequency than humans could hear. And that's for basically black holes that are about 1 million times the mass of the sun, give or take. But in some really large galaxies, we know that there are black holes that are even 1 billion times the mass of the sun. And even LISA won't be able to detect frequencies that low. And so you can think of these different wavelengths or frequencies of gravitational waves in the same way that you think of electromagnetic waves. We have light that we see in the visible, but we also have radio waves that are very much longer wavelength. And we have X-rays that are very much shorter wavelengths. And all of them bring us different information about the universe around us. So far, we have managed to just about crack open this window, but only in a very narrow range of wavelengths. LISA is slated to launch in 10 years, so stay tuned because launch timelines have never slipped in the history of humanity. And hopefully we will be able to see binary black holes at the supermassive scale merging, but we could also see stellar mass black holes like the ones that might be in active galaxies or inactive galaxies merging with their supermassive black holes, because the only thing that gravitational wave detectors really care about is the frequency, and the only thing that determines the frequency is the total mass. And so 2 million or 1 million and 10 is basically the same. So we can see all kinds of really exciting things using these using this sort of middle detector here at these somewhat lower frequencies. The very most massive binary black holes from very, very supermassive black holes are detectable only at the very lowest frequencies, all the way over in yellow on the graph. And it turns out that you need arms that are so long to detect those wavelengths that you actually need something not even in our solar system, but you need to make measurements of lengths between us and the nearest pulsars. So we can actually turn our entire galaxy into a gravitational wave detector, and this is what the International Pulsar Timing Array has done. Pulsars are neutron stars, dead, massive stars that are spinning at very high rates, and they are spinning so fast that they are extremely stable clocks. They are actually better than the best atomic clocks that we have. And so as they send out pulses of radio waves, when those radio waves arrive, that travel time tells you how far they went. And because we have them in every direction on the sky, we can wait for a gravitational wave to pass through our galaxy and disrupt the timing of the pulses as they arrive here at Earth, and use that to figure out where there might be supermassive black hole binaries of the very most massive galaxies. Right now, you can see here on the graph, these are sensitivity curves. So basically, if you're above the black lines, that's good. If you're below the black lines, you need to get more sensitive. And so you can see that the IPTA line has maybe detected something called the stochastic background of gravitational waves, which is sort of, if you imagine you're out in the sea and the waves are coming from every direction and you kind of don't know where everything is coming from, but there's still like a notable bob on the ocean. That is the stochastic background, because there's so many binary black holes coming from every direction. We think that we have just about detected this stochastic background, but we can't point in any given direction and say, there are 2 billion solar mass black holes merging right now. But we're very, very close, and I would expect, again, in the next 10 years to be able to tell you, the amateur astronomers, check out that galaxy. It's pretty exciting. The other thing that I want to point out is that when gravitational waves come through, because they are changing the length of your ruler, the first time I had to give a gravitational wave talk to the public about 10 years ago, I sat down and I said, well, I want to figure out how to give everybody a tabletop feel for how much these gravitational waves are changing the lengths of rulers. And people know what ½ an inch looks like, or a centimeter, something like that. And I said, well, how long a ruler would I have to make in order to make the gravitational wave that was first detected, GW 150914 up there, make my ruler change length by about ½ an inch? And it turns out that I would need a ruler that would go all the way to the pillars of creation. If that helps you conceptualize it, congrats, you're doing better than me. The engineering achievement of these gravitational wave detectors is frankly spectacular, and it was one of the greatest privileges, I think, of my life to be able to go and see them in operation. The engineers have worked absolute miracles. And that is how we know about things in our universe, because the waves are there, we just have to have the wit to catch them. And so I just want to leave you with this thought that we have a new messenger that we've just begun to try to use to understand our universe. And we're going to use it to learn things that we didn't even realize that we didn't know. But the way that we have done that is through the structure of science, which is an enormous community. The engineers, there are about 1,000 people who built LIGO and worked on it over 40 years with no detections for 40 years. You all paid for that, and thank you so much. all of the light that we collected, that I showed you pictures of up here, you paid for that. You paid for Hubble, you paid for JWST, you paid for Chandra. We hope that you will continue to pay for these amazing discoveries, because curiosity and collaboration are what make us better people and teach us wonderful things. Thank you.
Part where everybody shouts questions, but preferably in order. So let's.
Can you attempt to describe for me how we've corrected for the seismic activity in these detectors?
Yeah, actually, that's a really fun one.
Please summarize the question for the video.
Absolutely. So the question was, can I attempt to summarize how we've corrected for the seismic noise in the detectors? So one answer is that the Earth is most active at particular characteristic frequencies, which is why this 10 hertz wall is like we just got to leave the planet. And indeed, people have proposed building detectors on the moon, because the moon, although it is also somewhat seismically active, has different natural frequencies, right? And so some of it is that the natural frequencies are, not so bad in this prime territory, but that's not to say that there isn't actually some very active seismic mitigation going on. In the LIGO control rooms, they had to put the control room at least, I think it was 10 meters away from the nearest part of the detector, because if they didn't, then the operator walking around with their mass, right, moving, would actually affect the measurements. You can actually tell the weather using the LIGO monitoring channels that are compensating for air masses that are moving in, waves that are hitting the coast. And my favorite one is in Louisiana, there's a forest where they do logging. And so if a tree falls in the forest, LIGO will hear it. No joke. Yeah, so the answer is a certain amount of suspension and a certain amount of active correction, knowing, because they've got basically wind monitors, like they have monitors, and they're sort of back correcting it out. And sometimes it fails and it's a mess. And they also have certain advanced warning systems, because obviously if there was a really bad quake, everything would shake. And so, I think like in San Francisco, right, they have like gas shutoffs so that, okay, we're just gonna turn everything off. And so like they just disconnect everything and turn everything off so that things can't swing and hit in bad ways if there's a big quake. Yeah. Yeah?
I've only read the abstract on this, but a couple of days ago, there was a paper in Physical Letters that said that current research suggests that with LISA, they'll be able to detect a solar mass star orbiting with a black hole.
Mm-hmm.
So my question is, can you talk to, like, are we at the threshold of that kind of sensitivity?
Yeah, so the question is if LISA will be able to detect a solar mass orbiting around like a supermassive black hole. And the thing is, basically, LISA is being built right now, and it is not yet launched. And so the launch date is currently slated for 2035. And I have asked the people who are in charge of keeping us on target, and everybody has said we are currently on target for 2035. And if you have ever had work done or worked with a contractor, I advise you to keep that in the back of your mind evaluating the launch date. But the goal is 2035, and we're probably not going to miss it by that much. The technology test bed, very excitingly, so the way that LISA is going to work is you don't want to build a tube that's millions of miles long, so you don't. Fortunately, space is a pretty good vacuum, so you just have 3 free flyers, and they shoot lasers at each other. And like literally that is how LISA works. And so to test how well it would work and how well we could control the lasers and how well we could measure things, they launched one like 10 years ago, and it performed exactly bang on better than spec. And so all we need to do is build 3 of them and launch them and control them accurately, and that should be fine. So, you know, yeah. I think that we have the technology, but we actually have to get the metal cut and the things built, and it's all custom, right? I mean, okay, we're building 3, so it's not exactly 1, but it's a pretty tough job.
With the LISA array,
Mm-hmm.
I'm just wondering how they maintain stable positions. Do they put them at Lagrange points, or?
So the question is, with the LISA array, how do they maintain stable positions? Do they put them at Lagrange points? And the answer is they don't maintain stable positions. They don't care exactly how long the arms are. Their job is just to measure how long the arms are. And so, of course, it does matter, right? If you're in a super unstable neighborhood, that's not so great. So yeah, they are going to be orbiting, they are going to put the 3 of them up at a Lagrange point so that it's not wildly unstable. But one of the things that they decided early on is that they don't have to control the length of the arm, they just have to know what it is.
So the timing is short enough on the blade.
Yeah, they're constantly firing the lasers, and yeah, they have a constant monitoring of the distances. Yeah. Great question. Yeah.
Like you have the 2 that are on the Earth that are exactly the same,
Mm-hmm.
but you're sending one up in space. How are you going to measure it coming back?
Oh, very well observed. So the question is, we have 2 on the ground, but we're only going to be sending 1 up into space. And so how is that actually going to work? And the answer is in some ways, not quite as well as the 2 on the ground. So we are cheating a little bit. You'll notice that the LIGO detectors, as well as the Virgo detector and the CAGRA detector, and also it's not built yet, but it is under construction. There's going to be a LIGO India, hopefully, in the next few years. Those are all at right angles, so they're all L-shaped, which means that you can only detect a gravitational wave that's coming in the correct direction, right? So if you're tilted in exactly the wrong way, then the wave comes through and it changes the lengths of things that you're not measuring. LISA is going to be an roughly equilateral triangle, and so you have to be really careful about doing your trigonometry, but basically you now have information that you get multiple lengths, and you get it in multiple directions. And so that's basically how we can get away with just flying 1, because that's going to be hard and expensive enough, and they definitely weren't going to let us fly 2. We did ask. Shoot.
And the other one's just, besides the supermassive black hole mergers that we're measuring,
Mm-hmm.
so we're talking about primordial black holes, right?
No. So, okay, so the question was, or maybe is there more?
No, where are we measuring these black holes at?
Sure. So the question was, the supermassive black holes, are they primordial black holes? And the answer is that they are not. So primordial black holes, so let me back up here a second. I kind of told you where the stellar mass black holes that LIGO is seeing, where they come from, right? Stars die, and they collapse, and you get a stellar mass black hole, and then maybe you get a bunch of them, and you build them up, and maybe an AGN, and then you get bigger black holes, and so, okay, we've got maybe explanations for all of those. But I kind of glossed over the fact that there are million and billion solar mass black holes, and I did not say where they come from. We do think that that supermassive black holes do live in the centers of every galaxy. We can really obviously see the evidence for the one in the center of ours, and we have other evidence for pretty nearby galaxies that works out pretty well. And so we think that there are these supermassive black holes in the centers of galaxies, but we actually don't know how they got there. This is an active topic of research. As we look with JWST, we can actually see evidence for active galaxies that are millions of times the mass of the sun. just a few billion years after the Big Bang. And we also see evidence basically about 300,000 years after the Big Bang that there's a pretty uniform spread of matter. And so there weren't supermassive black holes at that time, because if there were, you would see more distortions in the map that we don't see. And so somehow you have a very short amount of time to get 1 million solar masses into a black hole. And it's actually quite hard. You can keep feeding black holes gas, but if you do that, that tends to make them light up, and then we should see light from them, right? So we don't know what you start with. How big do you start your black hole? You can reasonably expect a pretty massive object to sink to the center of a galaxy, so it's not super weird that we find them there, but like, how did you grow that thing is really unclear. But primordial black holes are hypothetical objects that are formed from fluctuations in the vacuum energy density early in the universe, and basically you can hide small black holes in that cosmic microwave background map, but you can't hide supermassive ones in there. And so any primordial black holes, if they exist, would have to be quite small, actually, but not too small, because if they're too small, then they evaporate. So there's this like set of masses that you can potentially have primordial black holes at, but it's very limited by our observations of different wavelengths of light for the most part. And so there's actually a pretty tight band on that. And in fact, people do look in the LIGO signal for black holes that are smaller than the mass of one sun, because anything smaller than the mass of one sun can't have come from a dead star. It has to have come from a primordial black hole. And so if you manage to get two of those into existence and together, you could actually see them using LIGO. And so people actually do look. But so far, no dice. Do they have life expectancy? And by that you mean LIGO?
No, I mean the black holes.
Oh, the black holes. So black holes do have life expectancies. They are extremely long. It turns out that if you leave a black hole out, it will sit there and it will take in more stuff because gravity always pulls. And so they tend to increase in mass. But you might have heard of a thing called Hawking radiation, which black holes can give off energy. And I won't go super deep into the process unless you really want to know. But basically, they can give off energy. Energy is equal to mass. So over time, they can evaporate. But in order to evaporate, they have to actually be hotter than the environment that they're sitting in. And the environment that we're sitting in right now, if we weren't here on the Earth, out in interstellar space is about 3 degrees above absolute zero, and that is so hot compared to the temperatures of even 5 times the mass of the sun, stellar mass black holes. And this is why, so really, 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 the smaller your black hole, the hotter you are, which is a little bit weird, but nevertheless the case. And so this is why really, really little black holes, if they were primordial black holes that were very small, about the size of Mount Everest, they would have evaporated by now because they are actually hotter than 3 degrees above absolute zero. But everything that's more massive than that is actually colder than the universe, and so they're absorbing light, and that means they're absorbing energy rather than giving it off. As the universe ages, the universe will get colder, and eventually that ratio will flip, and so then they can start giving off mass, and then it will still take them a really long time to evaporate because they're very massive. And so we're talking millions of times the age of the current universe. Yeah.
Okay, so with gravitational waves, since we've recently discovered how to
That's a really great question. So, right, dark matter is another thing that we don't see with light by definition, but we do see its influence because it has some kind of gravitational pull. It doesn't appear to be dense enough to give off gravitational waves. So this is why we're basically only looking at dead stars. But some people have suggested that there might be a way for a certain massive black hole to make up the dark matter. Again, this would be from primordial black holes, and so again, maybe there's a chance that we could use gravitational waves to see them, but mostly I think we're reliant on the fact that because dark matter has mass and it moves mass around, which can be light or dark, if it's light, we'll just watch it move the stuff and we'll figure out what it's doing. Yeah.
We're talking about the merging of black holes causing these gravitational waves. I was wondering what actually causes the waves. Is it them spinning around before they merge, or is it the actual merger?
Yeah, that's a great question. So it was the merger of the black holes is what's causing the gravitational waves, or what is really causing the gravitational waves? Is it them spinning around each other? And I think the best way to think about it is this diagram over here where you have two black holes that are orbiting around each other. And so as they're changing their position, you can imagine if you were really close to them, you would notice because they would be moving away from you or towards you. And so you would feel a stronger or weaker gravitational pull. And that's that like corrugated kind of wavy looking thing that you see. And so the reason why the gravitational pull that you're feeling from them changes is because they're orbiting around each other and changing their distance to you very, very slightly. And if you are really close to the system, it's actually very violent, but we're really far from the system. And so, you know, it's sort of like a tsunami happens in Hawaii and somebody on the East Coast will get a little, you know, ripple like that. So it is this changing orbit that is in effect causing the gravitational waves. Yeah. Does that? Oh, yeah.
I was curious about using the pulsar array to get the stochastic background of, you know, you said it's kind of like the small little waves in the ocean a little bit because there's so many different kinds of mergers that are happening and you don't know which way. Could that be like potentially used as like a way to measure like the expansion of the universe, as in like those little small waves maybe get a little bit longer in time difference from between each other, or is it so random that you can't really take any kind of pattern of it to get the expansion of the universe?
Okay, so that's a really cool question. And so I'm going to try to repeat it. Basically, when we have the pulsar timing arrays and we're seeing this sort of combination of all of these waves from everywhere coming in, and we're just sort of getting this like mess of burbling, could we use it to measure the expansion of the universe? Because the things that are farther away will have given off waves at some wavelength, and then that wave will have been stretched more as it had to come farther to us. And so like, could we use the shape of the burbling, like how much is at different frequencies, for example, to try to help measure the expansion of the universe? And the answer is that I don't know. So it's a really good question, and it's not one that I've thought about specifically before. And I'm pretty sure that somebody has, because people have thought about how to use gravitational waves to measure the expansion of the universe, but not so much in the stochastic background. People are still arguing over what, you know, there's a line on here, right, that says like, oh, this is how much intensity you have at different wavelengths or frequencies, right, as though like this is what it is. And like people are still arguing about whether we even know that shape super well, or the level super well, like the error bars are very large. So I think it's, so if it's possible, it's not possible right now. but what people have thought about is if you can get both light and gravitational waves from the same place, and you know that they came from exactly the same place. And this has happened once, because we did see 2 neutron stars crash into each other, and those are not black holes, and guess what? They give off light. And it was a pretty spectacular event. Literally 3,000 astronomers were on the paper about this thing, which is about a third of the entire working population of astronomers worldwide. It was the worst kept secret on the planet. And we got light from the neutron stars colliding, and then we also got the gravitational waves from LIGO. And what that enables you to do is that gravitational waves enable you to measure a distance, because the frequency that you measure is specifically tied to the mass of the objects, and you know, therefore, the mass of the objects just from the frequency. And if you know how massive they are, and then you tell how massive how strong the wave is, then you know how far it came, just in pure distance terms. And then if you see some light rays from the same source, and you know it's the same source, you can go out and get a spectrum, and you can then measure the redshift. And so then you know how fast the object is moving away. And so now, for those of you who are astronomers, you will realize that you have V and D, and so then you can make a Hubble diagram, and you can measure h naught, the Hubble constant, the expansion speed of the universe, because you just have 2 totally great measurements. There's still error bars on all of those measurements. The distance is subject to the uncertainty of the inclination angle of the system. And so one measurement is not good enough to, it's between 50 and 100, which is something that I knew when I was an undergrad, right? And that was still sort of controversial, but still everybody agreed. So we need about 10 objects like that to really get a good measurement of the expansion speed of the universe. And unfortunately, we haven't gotten we've gotten other neutron star binaries, but we've never seen the light-based counterparts to them. And there's a big debate about why that is. A certain amount of recriminations as well, which is why it would be great if the binary black holes were coming from AGN, and we could determine that there is an electromagnetic counterpart there. And so then we can do, basically the method doesn't care what kind of source it is. This can also work for LISA sources. If you see a binary black hole merger and it's happening inside an AGN, that will definitely have some kind of light-based counterpart, and so you can do that trick there as well.